So let's say you want to interface with Twitter, Facebook, LinkedIn, whatever social network, but you have a problem because third-party interfaces in general are hard. Lots of reasons for this. Just a few are that they are slow. It is so much slower to call an external service than anything that you have internally, even the hard disk that Eric was showing last presentation. But users don't understand this, right? They want results right now. They can see their friends instantly on Facebook. Why can't they see them on your site? Why are you slowing down what they're trying to do? Another problem is that third parties always have rate limits. These vary widely from one service to another. There are all kinds of weird corner cases and rules, and some don't even publish their rate limits, like Facebook, so you have to deal with them reactively rather than proactively. This causes a lot of problems. Instability, yes, even Facebook goes down, so you have to deal with outages. You have to deal with random failures, 500s, 503s, fail whales, all the kinds of stuff that in your internal system you work really hard to work around. You are confronted with them head-on in third-party interfaces. So luckily, there is a really great tool built for the Python community, first integrated in Django, then split off, called Celery. It is a distributed task queue, essentially. And so you have chosen to use Celery because it is asynchronous, which means that you don't have to do all of your third-party interactions within the request-response cycle. It's distributed, so you can spin up pools of workers as you need them, shut them down when you don't need them anymore. It's fault-tolerant, it has retry built in as a feature. You can fail safely and still maintain your normal workflow. But now you have two problems. Actually much more than two up there, but these are all design problems that come with dealing with distributed systems, and Celery is no stranger to these kinds of problems. Before we dive into each of these design issues, you may notice throughout the course of this presentation that I have pretty strong opinions about what you should and should not be doing with Celery and how you should do it. You can feel free to trust me at my word, or you can grow me later, but one thing I will say up front: always use RabbitMQ as your broker. Never use RabbitMQ as your results store. You will be so much happier if you just follow these rules. RabbitMQ has ACK support. It has built-in exchanges and queue bindings and all kinds of routing features in it. It is meant to be used as a message queue, unlike Redis and all those other backends that Celery supports. RabbitMQ, however, is a terrible result store because as soon as you ask for the result once, it's gone and you can never ask for it again. So if you have a distributed system that's checking for when things are done, one place asks for it, it says, yeah, I'm done, or no, I'm not done yet. You ask for it again somewhere else, and what task? I don't have a task. That is not what you want from a result store. It should store the result. Okay, so let's get on to organization. You want to try to make your tasks small and as atomic as possible. The idea here is that workers are ephemeral units. You should be able to kill them at will, spin them up at will, and you get much better distribution from small tasks. You can spread them out better, parallelize them, and you should preferably only make one third-party call per task. If you have more than one API call, say you burn through the first two, you fail on the third one, you now have essentially lost two calls from your rate limit with no effective work done, provided that you need that third to complete your task. If you separate them all and use a dispatcher to call each one either in series or parallel, then you keep each stage of your work as you go along, and you get, like I said, better distribution. You want to try to keep task arguments to a minimal state. A lot of reasons for this, but for instance, model instances, you should pass the PK of the model rather than the model instance. Celery is actually serializing that full model instance, sending it up to your broker and back down to the workers. You don't know how long that's going to take, and in the meantime, you could have deployed new code that has a migration, say, so now your model instance state is out of sync with the actual model definition in your code base. Lots of bad things can happen. So you will avoid all of this, and you will minimize the size of your messages, which means less memory overhead and faster message passing if you only use minimal state in your message definitions. You should defer data access to the task itself, again, for the same reason, because you don't want a lot of information going over the queue. Like I said, it increases performance and it prevents serialization, synchronization issues. So let's look at an example task. This is a bad example. It passes in a model instance, as I said not to do. It makes several API calls in series in the same task. And when it tries to save the model instance at the end of the task, you could blow up here, as I've mentioned, because you are now working with a deserialized instance of a model whose state is completely undefined in relation to the database that you're working with. Instead, if you pass in the model PK, you can avoid any race conditions by retrying if you get a do not or does not exist exception. This is actually good. It helps you maintain reality with your database. And then you can use your task as a dispatcher for several API calls and get them all done in parallel. So, as much as Celery tries to hide it from you on the surface, tasks are classes. You may define a function, but as soon as you decorate that function, you've made it into an instance of a subclass of task. Tasks are just classes. Don't be afraid to subclass them yourself and make abstract parent task classes to encapsulate common functionality that you need for a lot of your tasks. So if you were to take, say, this task as an example, it does a lot of boilerplate stuff that you'll find that you're going to do over and over again between different API calls, for this, in this instance to Twitter. Instead, if you make an abstract task-based class and you wrap all that function up in, say an API call function, and then you just return the result of whatever your client were to give you, then you can make a subclass of that, take away a lot of that boilerplate, and just use that API call function over and over again. That has other benefits that we'll cover later. The final recommendation for organization is to make tasks idempotent when possible. Tasks will fail. You cannot stop tasks from failing. They will fail in creative ways that you didn't expect. It's a very easy fix to say, just run that task over again, rather than to say, oh, well, we were in some unknown state halfway through the task, so we have to patch that up, try to manually get it to the end result. It's not always possible, of course, because you may have database rights that are not replicable. You may have rights to your third-party services, but when you can, idempotence will save you grief. So let's talk about task distribution. Every third-party service you're going to work with is going to have pagination of some kind when you're retrieving a list of resources. And pages are very logical places to break up your tasks because they're essentially instances of a for loop. You're doing the same thing over and over again. That says to me distribution. So the strategy is different dependent on whether you have access to limit offset through the third party, or whether you're dealing with a cursor that you get a value of a cursor for each page and you call it with the next value of the cursor. Sometimes you don't even know the total size of the set you're working with, so that can change your strategy as well. So provided that you have the best case where you have limit offset and you know your set size, then the easiest way to handle pagination is to have a dispatcher task that instantly dispatches every single page that it's going to need to, however big your set size is. And so you get 100, 1,000, 10,000, whatever tasks dumped on the queue at the same time. The workers churn through them furiously fast, and provided that you don't hit rate limits, you get really fast import of large number of objects from a third party. That is very little code. This is the dispatcher that just goes through the range of offsets and launches pages. So let's say that you do not have limit offset support, in which case whether you know the set size is irrelevant because you can't launch page 2 until you've done page 1, because page 1 includes the cursor value used to launch page 2. So it still makes sense to do this in separate tasks because you get to save the bit of work from page to page, but you can't run them in parallel. That will look something like this, where there is no dispatcher. The task itself dispatches the next page, and you start out with the default cursor value of whatever 0, whatever the first one is, and you look for a sentinel cursor value that tells you you're done. You launch one page after another, until you get to the end. So let's say you do have limit offset, but you don't know your set size. This is the case for, I believe, LinkedIn actually lies about the number of friends over a certain amount, and things like that. So you create a dispatcher task, you determine how many concurrent pages you want to launch at the same time, And then you have one page leapfrog its other concurrent pages and request the next in the set. So page 1 will request page 4, page 2, page 5, on and on, until you get to page 6 over there, which doesn't have any results. And so it says, there are no more pages, I'm going to stop requesting more pages. The downside to this is you make API calls you don't have to, because pages 7 and 8 could have been skipped if you ran them all, as the previous example, one page launching another. The upside is you get the parallelization in your distribution, multiple pages at once. So the dispatcher for that method looks something like this. You set a number of concurrent pages, and for each of those in the range, you launch a single page, and then from within that page's task, it looks for results. If there are results in that page, it then increments itself by the number of concurrent pages and launches that next page. Pagination is not a science, it is an art. You'll find, based on varying degrees of variance in response times from social networks, that sometimes a social network will say, like Facebook will say, I can support 5,000 of these per page, and they'll time out if you ask for any more than 3,000, for instance. Sometimes you're bottlenecked on your database rights, and so you can't actually finish a page of results in a good amount of time. Your goal here is to minimize the number of API calls over the set of pages, but you may have to make your page size smaller than the maximum in order to get tasks done in a reasonable amount of time. Remember, you need to minimize the state in your task definitions, so it's a very bad idea to say request all of a person's friends in a single task, and then just pass off thousands of friends in messages to other workers, because you'll get megabytes of message sizes that have to live in memory in Rabbit, and you'll eat up your memory real fast. Rabbit's a little bit better about that these days, but there was a time not too long ago when Rabbit would just flat out like hard crash if you ran a memory. No warning, no nothing, just everything's gone. That's bad. You want to set a timeout on your task. Celery gives you a way to set a soft timeout and a hard timeout, so that you can deploy code easily, so that you make sure that you know when you have long-running tasks, and you can go and fix that. And it's a problem that you know about, so you can solve. Another problem with task distribution is dependency. When you have tasks launching tasks, it's very hard to answer the question, am I done with this set of work? Because you have this dependency graph, and it could be a very complex graph depending on how your tasks are structured. Luckily, Celery 3, if you haven't checked out Celery 3 yet, a major version release not too long ago, it has a lot of good features. One feature it has built in is this dependency graph tracking. When a task launches a task, that child task says, okay, this is my parent task. That gets serialized into the results store, so you can ask for the full graph of tasks if they've been built. And if not, it'll raise an exception, and you haven't built out your full graph yet. And then you can go through and check the result state of each of those tasks to get an answer to, am I done yet? So this requires that you don't ignore the results, because otherwise there won't be anything in the results store. And re-emphasizing, do not use RabbitMQ as your result backend. If any of you take anything from this presentation, it's do not use RabbitMQ as your result store backend. Please don't. So now let's talk a bit about rate limiting. Problems with rate limiting, well, the first problem is that Celery's rate limit feature probably doesn't do what you think it does unless you've actually looked at it and used it directly. We'll get to that in a minute. Third-party rate limits depend on many different factors. They can be unpredictable, they can be complex. You have to be able to deal with all of those factors if you want to respect third-party rate limits. So we've got a little sample task here. It's as simple as I could possibly make it, and it's rate limited to run once per hour. And it's important that it only run once per hour. I'm going to now do a live demonstration to show you how Celery will handle this rate limit. So the same things that I just mentioned. It doesn't work with multiple worker daemons. It doesn't maintain its state between daemon restarts. Luckily, our rate limits we're wanting to deal with are actually enforced by the third party, so we only have to make sure we're respecting their rate limits. We don't have to enforce our own. And the net is you want to use your own external centralized store for rate limiting when doing tasks and not Celery's built-in support. Redis is really good at this. It has a lot of data types that we can use. The factors can vary based on who's asking, what feature they're asking for, whether it's public or private information, all kinds of other unknowns. The best case scenario is that all these are published. The reality is, even when they're published, they're usually not consistent. So here's just an example of 2 calls to the Twitter API. The first one is just getting your profile settings. You can see it gives you a rate limit class. These are all HTTP headers, by the way. It gives you a class of API identified, a certain rate limit, and a time when that rate gets reset. You call the same API but a different endpoint, the search endpoint, and you see these feature rate limit class for user search. Has a completely different rate limit and a completely different reset time. Twitter is actually going to be rolling out more of this with 1.1. And so you need to be able to react dynamically to these rate limits based on the factors that they depend on. So there are a few strategies here. When you have known rate limits with a fixed time window like the one I just showed you, which means that you have 350 calls per hour, and at this Unix timestamp you get your new set of calls, there is a simple way to deal with it, which is you just keep calling things until you hit the rate limit. Once you hit the rate limit, you inspect the headers to say, when do I get more calls? You stick that timestamp into Redis, everybody looks for it, and they delay themselves until you get your new batch of calls. If you need to answer to the user, how many calls do I have left this hour? That's a little bit harder, and you have to use a counter and either increment from 0 or a decrement from your initial rate limit until that timestamp passes, and then you can reset it. So we're going to show you the simple solution, which is just see if the Redis key exists. If it does, pull the timestamp out, subtract from now, and retry with a countdown equal to the difference so that you won't retry until you get your new batch of tasks. If you don't see the key, then you try the call. If you get a rate limit exception, then presumably your client is nice enough to tell you when you are getting more calls, but if not, you need a better client. And then you, same thing, you just figure out how long it is in the future and do a retry with a countdown until that happens. If you know your rate limit, but you have a rolling time window, for instance, like 25 calls every 2 hours, which incidentally is Facebook's unpublished rate limit for wall-to-wall posts, you can use a Redis sorted set of timestamps and remove any stale ones from the end, or from the beginning, that is. Check the length, and if the length is less than your max number of requests within that window, you're free to make another request. Otherwise, you have to wait until the oldest one would have dropped off the window in order to make more requests. So that essentially looks like, there we go, like this, where you have your window, you have your expiration time based on the current time minus that window. This all Z, rem, range, whatever, that's all Redis sorted set functions. They're really useful, so you just chop off all the instances of the set whose score is lower than the expires time, and then you do a Z card to find out how many there are in the set. If there are less than your max, you're free to make another call, and you add yourself to the end with the current time value. Otherwise, you determine what time stamp the first one has. You determine how long that is in the future for it to roll off the expires window, and you retry with that countdown value. So if you don't know the rate limit at all, you have to be reactive instead of proactive, using something Google calls exponential backoff, which means that once you hit the rate limit, then you start incrementing a counter that acts as an exponent to the number of seconds that you should wait to retry. So you're hammering Google or whoever really hard at first. They start to rate limit you, and you back off by 2, 4, 8, 16, 32 seconds until you reach a maximum ceiling. And then once you start to get through again, you can either chop off your counter and go back to 0 and open up the pipe instantly, or you can gradually decrement your exponent counter and kind of soft go back into it. Which you employ depends on how nice you want to be and what they'll let you get away with, honestly. So an implementation of that is here. You get your exponent. If there's not an exponent or if it's 0, you go ahead and make your call. Otherwise, you retry with 2 to the back off exponent seconds. If you try to make your call and you get rate limited, then you increment this key and you do the exact same retry. You'll see a common pattern here is if you have already been rate limited, you implement your strategy. Otherwise, you try to make the call. If you get rate limited there, you implement the same exact strategy. So let's talk about failover. Unfortunately, we've been using countdown a lot here for failover with retries, but even countdown doesn't do exactly what you would expect with Celery. And third parties can, again, fail in lots of interesting ways, so you have to make sure your failover strategy is really solid, really tight. Gosh, I keep losing connection here. All right. So I would love to give you another code demonstration here, but my presentation is already really long, so I'm going to skip that. Suffice to say, tasks are immediately dispatched to a worker daemon on retry. They're serialized with an ETA of when it's safe to actually try that task again. The worker daemon hangs onto it in memory until that ETA is passed. It does some internal prioritization to determine when it should retry the task, and then it retries the task. You would think that you could lose the work this way, except that Celery tries really hard to make sure you don't on a soft shutdown, and Rabbit has an acknowledgement feature, so the worker doesn't acknowledge that it's working the task until it is actually working the task, which saves you from losing work, even if you were to kill -9 your Celery worker daemon. But this is still a very suboptimal solution because you have workers hanging on to tasks that should be in the queue. And so your centralization, or your decentralization strategy, your distribution strategy is totally thrown out of whack because you could have one worker daemon that has a whole bunch that is waiting to work and another that's starved for tasks at the same time. And this is not a good solution. So the solution to this that I've come up with, inspired by, there's a guy who wrote a blog post on this, is dead letter exchange is an extension of AMQP that you can employ to fake this kind of ETA support that Rabbit itself is missing. You have exchanges in AMQP that queues bind to with routing keys. And so you have a message that reaches an exchange, and then it has a routing key in the message. The exchange says, what queues do I have that match this routing key? I'm going to send the message to all of those queues, and then the queue can do what it wants to as far as consumers pulling off of it. In this case, we define an ad hoc queue with our default routing key, but in a separate exchange. That queue has a TTL with the amount of time that we want to wait for that task before it gets actually put into the main queue. In just an example, 60 seconds. And then we set this property on the queue called dead letter exchange to tell it what exchange to dump the message into after that TTL has passed. We don't hook any workers up to this queue. There are no consumers, so all the messages stay in the queue for the full TTL. They expire, and when they expire, they get dumped into this other exchange here, which is our normal Celery exchange. Has the same routing key bound to our default queue with workers consuming from it. And so at the end of the TTL, it goes through the normal process, gets consumed by a worker just as if it were newly sent. But all this time, the message exists on your RabbitMQ server, not in your workers. This is a snippet from an overridden apply async function from a task subclass that dynamically tells Celery about a queue that it's creating with these queue arguments of message TTL and dead letter exchange. You also see this X expires here. That basically ensures that the queue disappears after that number of seconds because we don't actually want to keep all these queues around. We just want them temporarily for the purpose of dead letter exchange. So then you update your routing options by telling it, route it to my countdown exchange with this new queue I've just created. And then Celery will dump it into the countdown exchange. It'll get routed to your queue. It'll sit there for your TTL, which is your countdown value, and then get dumped into the normal Celery process. So that is the alternative to using Celery's built-in countdown. I hope to convince Ask that this is worthy of putting in Celery itself. Again, third parties can fail in lots of interesting ways. So you want to figure out all of your edge cases and weird things that only happen once in a blue moon, wrap all of those up into a centralized function, stick it in a task-based class, and use that base class for all of your subclasses that use that same social network or third party to make those calls. This can include retry functionality. It can include, exception handling, all the things that make it really hard to wrap up your task nicely and neatly and make sure that it gets done or retried. You want to handle within a single function. All right, so dealing with multiple queues. Why would you want multiple queues? Well, you get better control over the priority of tasks if you segment your queue by task type or by priority, that sort of thing. You can allow for spikes much better because you can distribute your resources however you want to. You can launch worker daemon pools that only consume from certain queues rather than all the queues. And so you have many, many more routing options available to you if you use multiple queues for different purposes. Another interesting use case is what I call a trickle queue, which is when you have really low priority work, but maybe a large volume of it that needs to be done over a long period of time. And we'll talk about that more in just a second. It's really easy to implement multiple queues in Celery. It's just a setting in your settings.py. You define the queue name and the binding key. You can get deeper into this if you actually want to use the Kombu queue object under the covers in the AMQP implementation, but you don't have to. And then you just launch your Celery worker daemon with your queues argument. I think by default it uses all the queues, but it's always better to be explicit. So you can tell this worker pool use this queue, this worker pool use all the queues, and manage it however you want to. So back to the trickle queue. So let's say you want to do something like keep the avatars fresh for all of your users that have Twitter accounts connected. You want to do this for, say, hundreds of thousands of users, but you don't want to starve the other things in your queue. So you set up a cron job. You have a cursor persisted somewhere like Redis or in your database or something that says, this is where I last left off. It's been a minute. Just put 5 or 10 more in the queue and work them. It's very low priority, but if you dump all of them at once into your queue, then you're going to starve everything else that wants to use that same priority queue. So let's say you had Facebook people whose avatars you wanted to update as well. You dump 100,000 Twitter jobs in this queue, it takes days and days and days to work, and now your Facebook users have days old, stale avatars because you starved one task in favor of another, making implicit priority where you should have been having them equal priority by trickling them into the queue. So I mentioned a cron job just now to implement this trickle queue. This is another one of my strong opinions. I think Celery beat is a re-implementation of the cron wheel that doesn't need to exist. Don't don't use it. It has problems. One of those problems is that it uses a persistence layer, either the file system or the database, to keep track of your periodic tasks. That can get out of sync with your tasks, especially if you delete tasks and the record is still in the database. Celery beat will try to launch tasks that don't exist and then will yell at you. This is bad. It's just one more process to manage. Who wants to manage another process unless you're an ops guy and your job is managing processes? But I'm not. I don't like managing processes. So I like the fact that everyone in the world uses cron, and it's really just not that hard. There's no need to make a reinvention of it. There's no need to re-implement it in a way that could have bugs. Less code is good, right? So just use cron, don't use Celery beat. There's probably not actually time left, but I'm going to pretend that there is for the sake of this meetup and go right into debugging. Just a few tips. When you're debugging locally, go through the effort to set up Rabbit, Redis, set up your worker daemons, all of this stuff. I know it's antithetical to the run server way of doing things in Django local development, but you really don't want to use always eager to run your tasks synchronously when you're developing locally. A lot of these strategies have tasks launching tasks, the dependency tree that I mentioned. If you have like a big network that you're importing locally, you're going to exceed your maximum recursion depth. You're going to do other nasty things like incidentally launch a task that takes a long time to get all worked out, and you're waiting for your local web page to load for minutes and minutes and minutes while it's running in the background doing these things synchronously. That's not really designed to be done synchronously. And it's always better to be as close to production as possible when you're working in your local environment because things work more like production that way. So given that you have given up synchronous running of tasks, you now have debugging issues because problems are harder to track down. You can't easily just set a breakpoint, although you can set a breakpoint in Celery workers, but that's another problem. So logging is the answer to these issues, and it's good for production as well as your local environment. Add more logging. Info level logging doesn't get caught by default, so you can specify log level info on your worker daemon pools. But logging is really the central tool that you have to debugging a distributed system. And third, when you're working with third-party dependencies, unit tests are good, but you really want a suite of integration tests as well. There's an idea that you should never be mocking anything that is outside of your control, that you don't control the API for. And you don't control the API for third parties, but you mock them anyway, and I do too, because it saves time in your test suite, and you don't actually want to make those calls to live servers. I understand it's completely reasonable, but you're not actually testing the full loop until you have integration tests that actually go out and hit those live servers and third parties and make sure that the API that you coded against is actually the API that still exists. Or any number of other things that might have changed because you're mocking out these third-party calls. A few gotchas. This is just a basic Python thing, but if you're using C-level blocking like sockets, then nothing else is going to be able to interrupt your code. The soft timeout that Celery provides as a feature won't actually fire. You'll get to the hard timeout, which is just like a hard process kill, and you'll lose workers, and bad things will happen, and you won't know why. So the easy solution for third-party interfaces in particular is just to set a timeout on all of your socket calls. Make sure when you're using client libraries, most of them support timeout. Again, if they don't, then you should probably consider using a different library. But make sure that you implement that always. Soft timeout doesn't automatically retry a task. It doesn't know whether it should or not, so you really need to be trying and catching that soft timeout if you are implementing a soft timeout, which I recommend, to make sure that you're retrying if you hit it, because most of the time it's due to just a network being slow, your database being slow, something being slow that's ephemeral and it's going to go away, so you might as well retry that task. Another thing, and this is an odd design choice on Celery's part, is the default task result state is pending. So even if Celery has no record of that result whatsoever, either it's expired from cache or you've deleted it from the database or whatever, Celery will tell you it's pending. This is not very useful, but if you know about it, it's okay. Just know that if you set a cache expire time on your results and you get pending back as an answer, it's not because it didn't complete, it's probably because it either completed or failed and then got deleted from your results store, and Celery is just being helpful in telling you pending. So that is about it.